Welcome to The Explainer. Today, we're going to dive into a pretty epic drama that's happening all around us all the time. It's the story of how atoms, the building blocks of literally everything, bond together by giving and taking electrons, creating the very world we live in.
So, let's jump right into this with a really fascinating question. You've probably seen those crazy videos of pure sodium metal exploding the second it hits water. But here's the thing. That same sodium is in the table salt we sprinkle on our food every day. How is that possible? How can one thing be so dangerous and so totally harmless? Well, the answer is hidden in the world of atomic stability, and it's all about the powerful forces driving chemical reactions.
To really get this, we have to start with one main idea. Most atoms are, they're kind of restless. In their natural state, they're not very stable, and they are always on a quest to find a more stable, lower energy state of being.
Now, if you look at the periodic table, there's this one group of elements that has it all figured out. They're the noble gases. Think neon, argon. They're basically the cool kids of the atomic world. They're totally unreactive and incredibly stable. And why is that? Because their outermost electron shells are completely full. They're perfectly happy just the way they are. And this desire for a full outer shell, it's the driving force behind pretty much all of chemistry. It's such a common thing that it has its own name. The octet rule. At the end of the day, most atoms just want to have 8 electrons in that outer shell. They want to be just like those super stable noble gases.
This table right here just lays it all out. So look at sodium. It's got this one lonely electron in its outer shell. It is way easier to just get rid of that one electron than to try and find 7 more. But chlorine? Chlorine is so close. It's got 7, it just needs 1 more to have that perfect set of 8. You can almost feel the tension, right? So this desperate search for stability creates this really basic dynamic. It turns atoms into either electron givers or electron takers. And when they do that, they become something totally new, an ion.
The givers, like our friend sodium, are usually metals. So when that sodium atom gives away its one negative electron, think about it. It now has more positive protons in its nucleus than it has negative electrons flying around. So that atom isn't neutral anymore. It's become a positively charged ion, and we call that a cation.
And on the flip side, you've got the takers, like chlorine, which are typically nonmetals. When a chlorine atom snags that one electron it wants so badly, it suddenly has more negative electrons than positive protons. And just like that, it becomes a negatively charged ion, which we call an anion.
So there you have it. Those are the 2 main game plans that atoms use to get stable. Metals lose electrons and become positive cations. Nonmetals gain electrons and become negative anions. And this fundamental difference, it sets the stage for a pretty powerful attraction.
Okay, so the stage is set. We've got our positive cations and our negative anions. And now, an absolutely unstoppable force comes into play.
You know the saying, right? It's one of the most basic rules in all of physics. That brand new positively charged sodium cation and that negatively charged chloride anion are now powerfully magnetically drawn to each other. It's an electrostatic attraction.
This incredible force is what we call an ionic bond. It's the cosmic glue that locks these ions together, forming a brand new, super stable thing called an ionic compound. And this is how that explosive sodium and that poisonous chlorine gas team up to become totally harmless table salt. And let me tell you, this bond is ridiculously strong. That's why salt has a melting point of over 800 degrees Celsius. You have to pump a ton of energy into it to even think about breaking that bond.
And what's really cool is that it's not just a simple 1-to-1 pairing. In a salt crystal, every single positive sodium ion is perfectly surrounded by 6 negative chloride ions. And each chloride ion is surrounded by 6 sodiums. This perfect repeating 3D pattern is what we call a crystal lattice. It's what makes ionic compounds like salt these hard crystalline solids. But check this out. In this solid state, the ions are locked in place, so they can't conduct electricity. But the moment you dissolve that salt in water, those ions are free to move around, and that's what lets salt water conduct electricity. Pretty neat, huh?
Okay, but for this whole arrangement to actually work, for a stable compound to even form in the first place, there's one last absolutely non-negotiable rule they have to follow.
The final compound has to be electrically neutral. It has to have an overall charge of 0. So all those positive charges from the cations have to perfectly cancel out all those negative charges from the anions. They have to balance. So the question is, how do we figure out the exact right ratio of ions to make that happen?
Well, chemists have this really handy little trick called the criss-cross method. Let's take aluminum, which forms a +3 ion, and oxygen, which forms a -2 ion. All you do is you take the number from the charge of one ion and you make it the little subscript number for the other one. So that 3 from aluminum crosses over to the oxygen, and the 2 from oxygen crosses over to the aluminum. That tells us we need 2 aluminum ions to balance out 3 oxygen ions. And boom, you get the formula Al2O3, which is aluminum oxide.
And hey, this rule doesn't just work for single atoms. Sometimes you get these whole groups of atoms, called polyatomic ions, that act like a team and carry a single charge. But the rule of the game is always the same. You have to balance the positives and the negatives to get to 0.
All right, so we figured out how to build these compounds and how to balance their charges. Now let's learn how to actually speak their language.
The good news here is that the basic naming system is actually really logical. You just say the name of the cation, the positive one, first, and then you say the name of the anion. The only little trick is that you have to change the ending of the anion's name to "ide." So for NaCl, it becomes sodium chloride. Simple as that. But of course, chemistry always has a little curveball for us, right? What happens when you have metals, especially those transition metals in the middle of the periodic table, that can actually form ions with different positive charges? I mean, iron can form a +2 and a +3 ion. How on earth do we tell them apart?
The solution is actually pretty clever. We use Roman numerals right there in the name, in parentheses, to tell everyone exactly what the charge of that metal is. So, FCl2 is called iron II chloride because that iron has a +2 charge. And FCl3, you guessed it, is iron 3 chloride for the +3 iron. This way, there's absolutely no confusion.
So you see, this whole dance of giving and taking electrons, it's not just some abstract concept from a chemistry book. It's the process that builds the minerals in the ground. It's what allows the nerves in your brain to fire. Remember that whole conductivity thing? And it literally creates the substance of our reality. This constant push and pull for stability is shaping everything. It really makes you wonder, what other invisible forces are shaping your world right now?